So here we go. San Diego, California. There you go. There's my ITASCA sweatshirt I got on there. Sphere. Okay. Check this out. Granular material. We're going to do something where we want to model what's called GeoGrid. And we're going to, and I'll tell you all about what this is. But basically, this is this hard plastic stuff. And you put that into a granular system. And what it does is it strengthens it and it increases its stiffness. And this is what we want to have when we build a road. So what's a GeoGrid? There's my pocket knife. There's a reference scale. Okay, this stuff is plastic. It's extremely stiff. Comes in different sizes with different size apertures. This is granular material. This is actually the type of material that they put as what's called a base layer of a roadway. Let's see if I don't have the picture here. When you build a road, what do? You make a big ditch that might be, I don't know, 4 or 5 meters deep. Okay. And then what you do is you put soil in there and you compact it. And then what you do is you put aggregate in there. And if you mix these two together, that's a typical type of aggregate that would be used in Minnesota roadways. It's called ballast. And that might be, it might be a meter or more in thickness. And you smash that down with a compactor. And then you put your asphalt. The asphalt might be 6 to 12 inches thick. The ballast is hopefully stiff because the asphalt, when it flexes, the more it flexes, it eventually starts little fatigue cracks to grow out of the surface. Those fatigue cracks are bad because water gets in and it's a feedback mechanism, and then eventually your road starts to crack. So what you want is you want that ballast material. Ideally, it should be infinite stiff. So to make it stiffer, what they have found is they put a layer of ballast and then they roll this stuff on there. And then they put more ballast. This GeoGrid interlocks with the grains of the ballast. And when you just think, if you have a big pile of sand, and if you push it down from the top, it wants to dilate and bulk out. If you have the grid in there, when it tries to dilate, it gets restrained. So it's stronger and it's stiffer. And so what you can do if you have GeoGrid is you can make your roadways have the same amount of life, but you don't have to do such a thick layer of ballast. And instead you put the GeoGrid in, take care of some of that. Does that make sense? That's the big picture.
Yeah.
Okay. And this was a client from the Minnesota Department of Transportation who basically says in the field, practitioners believe that the GeoGrid gives you benefit, but the design code that they have to use currently is really crude, and it just says no matter what you have and no matter what GeoGrid you put in, you get to take 2 inches less ballast. And most people believe you could take substantially more reduction of ballast. And so this was some research work over many years that involved both field scale, lab scale, and numerical modeling to gain a better understanding of how the GeoGrid affects the stiffness, in this case, of a system. Okay. Again, the high level picture is we developed the ability to model unsaturated granular material. That means there's little, there's some water in there, and the water makes it stronger. Okay, and we'll talk about how we did that. We could model that material with GeoGrid. We could perform triaxial tests on it, and based on the triaxial tests, we can come back with what they call resilient modulus. It's kind of like it's the slope of that curve, basically. We could get strengths from triaxial tests. We did the dynamic cone penetrometer tests and lightweight deflectometer tests as well. If you don't know what they are, don't worry, I'll talk about that later. Again, do we have the mechanisms? With this system, we can quantify, because the model, what are the things you can change with the model? What are the things you can quantify the effects of, right? So we could change the geometry of this. Some grids are square, some grids have triangular openings, right? What is the fact to that? Some grids are really stiff, some grids are not as stiff, right? What about the ballast? We could change the shape, we could change the size distribution, we could change the modulus of the ballast itself. Packing process. The triaxial response of this system is highly dependent upon the initial porosity. And you can pack these things in different ways to get different initial porosities. Think of doing this with real dry sand in a laboratory, and you had a coffee cup and you had dry sand. If you pour the sand in very slowly and then take that and do a triaxial test on it. And then you go and in the next test, you pour the sand in, but then you pound it against the surface of the table a few times. Now it packs tighter. It's less porous. Then you do a triaxial test. You're going to get very, very different response. So we had a way when we construct this of controlling the initial porosity. And what we find is then what effect does that have on the strength? Again, what we find is the more porous, the weaker it is, and the less stiff it is. And then this unsaturated, what sort of moisture content, what sort of suction are we getting? What effect does that have? So those are the things that we were able to quantify with the model. Here's an example, putting in that geogrid, rolling it in. There's an example of the triaxial, they call it, geogrid. It's got 3 things. This one has 4. Okay. This is an example of an old-fashioned geogrid to support a railroad going across a swamp, right? You can see, you can get, a geotechnical guy, right? That thing is going to be able to bear the weight, right? It's a crude, old-fashioned geogrid. That's also what these are used for. If you have really bad material, swampy area, you can throw down a bunch of grid, then you can drive big trucks on it. Again, this is a bad slide. This is basically talking about that people really do believe that the geogrid makes it better, but the current design methodologies do not account for that. So the idea was to see if we could better understand geogrid so that we could propose changes to the design procedures so that people could take advantage of it when they do their design. And again, this is saying here 2 inches. That's what it used to be. If you have geogrid, it doesn't matter what shape it is, what stiffness, doesn't matter. Put in geogrid in the middle of the ballast, you can take off 2 inches. That's kind of ridiculous. That's so conservative. What did they do when they design things in Minnesota? It's crazy nowadays. They have one program. It's called MinPave, Minnesota Pavement Design. They have this program. That's what you have to use when you design a roadway to figure out the ballast, the thickness of the layers, the thickness of the asphalt. This program is crazy because it incorporates huge amounts of information. What do? You say, I'm going to design a road in northern Minnesota, which is by Lake Itasca, right? I said it's 150 miles north on the Mississippi River. It takes into account the fact that there's in general more precipitation in colder winters there than there is in Minneapolis. And that has an effect then on the life of the pavement. So all this stuff is embedded in this program. So in the end result of all this research was to provide new buttons, if you will, in MinPave, where you could say, I will have this type of geogrid and it has these properties, and therefore the MinPave will tell me what sort of thickness I can do. Okay. And so the way we did that was to come up with how does grid affect the modulus of the overall ballast. And the modulus is one of the most important things. The way that they do this design is they assume that they have an infinite half space that's made up of elastic layers. And these layers have a Young's modulus and a Poisson ratio and a thickness, right? So you could see you could do one giant elasticity solution for an infinite half space for this problem, and that's what they have. And so this is what they work with for their design, and they come up with different thicknesses and everything. These are inches, by the way. This is the typical traffic load. It pushes down, and what it does is deflects this. And there's 2 types of failure that occurs. You get horizontal strain here. This thing is pulling. This is a beam. It goes into tension, and every time you load it, there's little cracks that grow more and more and more as a fatigue loading. You might have 3 million cycles of load on a typical roadway until you reach 20-year design life. The other thing that happens is this soil starts to fail locally. And therefore, when this soil fails, this whole thing goes down, and you get what are called ruts. And I don't know, you may have seen those. Sometimes on bad roads, you get these ruts. They're going parallel with the direction of the traffic. So these are the 2 things that they compute with this infinite half space model. And what you have to do is you have to choose these things when you do a design such that the life you're going to get is greater than 20 years. So in Minnesota, the roads are built to last for 20 years. So the only way that we could affect the design procedure was we're going to affect the values of these modulus. The idea being just in this aggregate base layer, if you put in GeoGrid, how does this modulus change? And if this modulus gets bigger, that's going to make it last longer. Okay, so that's what we focused on. What's the effect on modulus? Okay, how do they measure modulus? If you have a granular material, what you do is you apply strain and then unload and then load and then unload, and you get this hysteretic behavior. And eventually, if you do this enough times, you get the same unload and load. And once you reach that point, you take this slope, this is stress versus strain, you take that slope, you call that the resilient modulus. The idea being that after you've had the road in operation for a few tens of thousands of cycles, it basically just behaves like this. And so that's the important modulus that you want to have. And so we developed the ability to do these models and to do this loading and to compute that slope. Okay. And with this, oh yeah, here's the last one. Here's then again, this is the type they do experiments in the lab. So this thing, I don't have a length scale. This thing is about a half a meter high. Okay. And they put the ballast in there. And then sometimes they put the grid in there and the ballast in there, and they measure these type of stress strain curves, and they compute this slope, which is the resilient modulus. Okay.